a 10-mile radius, we'll be able to tell. And in fact, I'm going to try something and be a little brave about it. I'll pass this iPad around. Of course, we're not going to drop it. Also, don't hit the stop record button. But you can take it and turn it around every which way and get a look at what the camera sees. I have only shot like a 2-second test movie. It has 220 gigabyte little tiny cards in it, and it just, so I expect I'm going to get home with this and try to process this movie, and it's going to take my computer, my fast computer, all night long to grind the movie together, and I don't know what I'll get. Please, at any point, feel free to ask questions. I'm going to focus this primarily on astronomy stuff, but the other thing of interest when we talk about science at the South Pole is just the South Pole itself. I actually, 2 weeks ago, I did a similar presentation like this for kindergarten kids at my old elementary school in Pennsylvania, and I asked them to come up with words, one word about the South Pole. And what did they offer? Cold. Cold, yes. And what did the second kid offer? Also cold. And what did the third kid offer? No. Cold again. And then eventually we got to penguins. But it's a really bizarre place to live and work. The first people to get there were actually, anybody recognize the flag? Norway, yeah. Raoul Amundsen and his team got there. And about 2 weeks later, they got there on foot. Very, very tough going at the time. About 2 weeks later, the British team got there. They didn't even know the Norwegians were in Antarctica, let alone trying for the pole. And they got there. Horrible walking, 1,000-mile journey. They got there, and there's a Norwegian flag stuck in the ground. Total bummer. And then they all died on the way back. Yeah, the story of that British expedition is really quite amazing. There's a one of the best travel books, and I've read a lot of travel books, called The Worst Journey in the World. Some other guys on that same British expedition, their job was to go out and get penguin eggs. Penguins lay their eggs in the middle of the night. And how long does the night last down here? Yeah, give or take, about 6 months. And their job was to go out in these horrible clothing, leather and canvas stuff. They had to, everything got covered in sweat. They were climbing over these giant icebergs. And they would, in order to put on their clothing in the morning, they would have to break it. It was all frozen. And in order to get out of their clothing and into their sleeping bag, they'd have to break the sleeping bags. It was so cold, their teeth fell out. The idea was if you could get a penguin egg, penguins were the most ancient kind of birds, not true. And they would bring this back to Britain, and they could look at the embryo inside the egg and figure out if penguins were the most ancient birds. And their guys that went to the pole died. They got back to Britain. Britain was in the middle of World War I when they finally got back, and no one cared about any of it. It was just the worst journey in the world. But a great book. The South Pole is on 2 miles of ice. Bedrock is about sea level, 2 miles of ice. Have any of you ever been altitude sick? Where at?
Not very high. It was up in Cleveland. We were dirt biking and we got to the top of the summit.
Anybody, anytime, no matter how fit you are. First thing they'll do with me, and I know because I went to the South Pole in 2002, get off the plane, take that first breath of minus 45-degree air. I'm gonna die. That's what everybody thinks. And they will sit us down for about 3 hours because everybody that goes to the pole goes with a very, very clear idea of what they have to accomplish over these 2 or 3 or 4 weeks they're going to be there, and they want to get to work right away, and that's a great way to get altitude sick. And how do you recover from altitude sickness? What's the easiest way? Anybody know?
Oxygen.
Down, even better. And there is no down at the South Pole. You're there. It's also, because it's so cold, it's extremely dry. Dry air is cold air. Cold air does not carry moisture. So although that looks like snow, the water in the air flash freezes. It is not like any snowflake that most of us have ever seen. It's like dust. And the longer I was there before, the more it started to look like a moon base. And the snow was like dust. You know that stuff when you open up the curtain and a beam of sunlight comes through and you see the dust in the air and you go, oh my God, that's what the snow is like at the South Pole. And it barely does that at all. It's really dry. So I think I'm gonna change gears here a little bit, and I've been doing this presentation in all over the place, in California and in Virginia and Maryland and Pennsylvania. And I'm gonna skip right to the astronomy, given our limited time. And whoop, there we go. Let me tell you about this. Lights, a little bit higher res.
Yeah, right over there. Getting close.
So on July 7th of this last summer, I was at Wisconsin, at the University of Wisconsin. We were working
That's my alma mater.
with, yeah, and the University of Wisconsin is the lead institution on this business that I'm involved with, the IceCube Neutrino Observatory. And I was with a group of students in an Upward Bound program, and I've been doing this and been involved with this for now almost 20 years. And we sat down with those students, and at the National Science Foundation, the principal investigator of IceCube and the chairperson of the National Science Foundation, huge, huge, huge announcement. Honest to God, as this was happening, I cried 2 tears. Yeah. Do I look tough? Yes. Nevertheless, 2 tears, because it was so amazing to see the trajectory of this thing. Here's what the announcement was and why it was so cool. Distant galaxy. In fact, we're talking about a galaxy in this announcement that is more than 3 billion light years away. At the center of most spiral galaxies, we now believe, there is a supermassive black hole, probably the result of the coalescing of individual black holes from individual massive star death. In many of these galaxies, the Milky Way, not so busy, but stuff is going to tend to fall into a black hole. Although, have we talked about black holes in this astronomy class?
Not yet.
Can I talk about the major misconception about black holes? All right. So, if the sun were to turn into a black hole right now, what would happen to the Earth? Don't say it would get cold, we know that. But what would happen to the Earth? What is the major misconception? What do you want to say would happen to the Earth if the sun were a black hole? It would get sucked in. But the black hole comes from the sun. Does it have any more mass than the sun had? No. Would it exert a stronger force of gravity? No, because you're not any closer to it. So in fact, the Earth would essentially continue to orbit. So a black hole is not per se a cosmic vacuum cleaner, but stuff does fall into our sun right now, and stuff will fall into these kind of structures. Now, some of the stuff gets jetted out at the poles. It's not like it went into the black hole and came back out. It's more like I turn on this sink full blast, 99% of the water goes down the drain, but some of it splashes out. It's not like it went in the drain and then came back out. It just splashed, right? These jets are like that splash. And these jets have intense magnetic fields, and they're extremely powerful. And what's the humanity's largest particle accelerator? Anybody know where that is? At CERN, yeah, in Switzerland, I heard it. This dwarfs that by a billion, bazillion, trillion times. And this thing was creating all kinds of particles, and we caught some of them in our detector at the South Pole for the first time proven. What is the messenger that we mostly use in astronomy to find out about the universe? Light, and light in all of its forms. There is, of course, visible light, but there's also the infrared, the ultraviolet, and the radio waves, and the X-rays, and the gamma rays, all that stuff. For the first time in your lifetime, in the last couple of years, we have started to do what we're referring to as multi-messenger astronomy. There's a big observatory that found out something about neutron stars coalescing. Does anybody remember this discovery? It was just about 2 or 3 years ago. No. Gravity waves. Yeah, remember that? They've already given the Nobel Prize for that. I know. Usually you have to wait 20 years to see if your project pans out. But at LIGO, there's a LIGO observatory out near Hanford. I was there last summer. They detected gravity waves. And they didn't just do it like, oh, let's look and see if we see some. They worked 30 years on that project. We've been working 30 years on this project. We had our big announcement in July. Did our main person get the Nobel Prize for this fall? No. It was this stupid optical tweezer lady. What good is that, using light to manipulate atoms? But we are hopeful. We're hopeful. So here's what we're catching. We are catching neutrinos, not light, but a completely different kind of particle, another kind of particle, not gravity waves either. But a neutrino is a really interesting tiny particle. While I say the word neutrino, right now, trillions of neutrinos went through your head, and none of them hit anything. Because that's what neutrinos do. I'm not saying your head is empty. It's full of stuff. But neutrinos just go, they're very hard to catch. In fact, we've just learned recently how to catch them. Neutrinos were invented to explain some things that were happening in physics. And it was 25 years later before anybody had any idea how to catch any way to catch neutrinos at all. And now we're catching them from a galaxy 3 billion light years away. I'm going to show you how that works. So I'm going to back up here. Whoop. All right. So our project is called IceCube, the South Pole Neutrino Observatory. I always like to put that picture up because my friend Megan actually worked in the front office at the University of Wisconsin, and several times a day she would get a call from somebody wanting to send a mixtape to this guy. No, we don't have his address, that's a different thing. This is our project. Our science lab on top of the ice at the South Pole, and down in the ice, we've got light detectors. When a neutrino goes through, and it does actually hit something, which happens how often? Not very often at all. It creates very faint light, and we have a whole bunch of light detectors in the deep ice at the South Pole. It's a telescope. The camera sees you if you close your eyes, remember that. You gotta learn to sleep there. A telescope, most of us think, oh, that's a tube and you look through it and it's got some glass in it and makes things bigger. Yeah, that is a telescope, but this is also a telescope because it catches things from far away and it tells you where they came from. But it's the weirdest telescope. There's nothing to look through. these things just get triggered. So if a light signal from a neutrino coming through this way, bing, 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 and we can retrace the path of the neutrino. It's really tricky business. The timing of these things has to be down to the nanosecond. That is 1/1000th of a second. And we've got about 10,000 of them in the ice. What do you think the ice is like down here? Any ideas? Hmm? Oh, cold, yes, penguins too, yeah. No. We actually have seen, not me personally, but apparently a couple times people have seen birds at the South Pole, but it's actually completely sterile. And if a bird was flying past the South Pole, that was not good for the bird. It was in a bad place, and things were not going to end well. So when the physicists who thought this up were sitting around over a beer, you're thinking, well, I wonder what the ice is like at the South Pole. Is that a good place to catch neutrinos? Well, we know there's a lot of it. The ice down that far down, a kilometer down, must be really dark. What is the signal that a neutrino is going to make, ultimately? Some very faint light, and so you want it extremely dark if you're going to have any chance of picking that up. And it turns out, although they asked glaciologists, hey, what's that ice like? How deep of a hole could you drill us? The glaciologist said, oh, I could get you down to, I don't know, we could get you down to about here. No, we want to get down to here. These are Eiffel Towers for comparison, by the way. Yeah, yeah. We could get you down. No, we're going to have to. So at the University of Wisconsin, they actually developed and invented the technology to make the holes. And that does not involve drilling exactly, but melting. Hot water and the technology that was developed allows the creation of a hole in about 36 hours. Hole stays full of water, 2 kilometers deep, and a string of light detectors gets lowered into it. And about a week later, all that water is refrozen and the detectors stay there for the next couple 100,000 years till the ice slides off the edge of the continent. It's stuck there. What we're putting in there are these digital optical modules, light sensitive part on the bottom and electronics on the top, and all of that data comes up here and comes back to us. It turned out that the ice was incredibly clear down there. It's the clearest stuff on Earth. We've tried this kind of thing in ocean water, but oceans are full of radioactive potassium, which gives off its own light. The ice is just beautiful. I actually had some of this ice. One of our scientists, Christian, came back on the last day I was there. We were having sort of a going away party at the South Pole at the bar called 90 Degrees South at the top of the dome. And he opens up this cooler and he's got these chunks of ice which are just as clear as, they're actually clearer than diamond. You know that crappy ice you get out of your freezer, it's got the air bubbles in it? Oh no. With pressure and time, those air bubbles, molecule by molecule, the air gets squished into the ice matrix, the H2O matrix, and disappears, and it's clear, and when you put it in a drink, it fizzes. The ice fizzes like Alka-Seltzer. It's really cool, yeah, really amazing. Here's essentially another view of the same thing. This did not all happen at once. Like I said, bright idea. Let's pull together a little bit of money from the University of Wisconsin and from some private donors and send a team to Greenland and see if they can melt a hole. And then we built a little one, and then we built a bigger one, and now we've got $500 million into this. And we actually have scientific results. When I was there in 2002, just for comparison, we were working on the sort of the final trial phase, and that was called Amanda. At the time, and I'm going to show you a movie that talks about this. There's a guy, and he's looking at a computer screen, and he pushes a button. He walks over to the printer. He gets a printout, and he walks over to a map of the sky. He goes, "Oh, yeah, right there." At the time, that process, we like to joke in this movie, that process from looking at the screen to printing it out to pointing to the sky, that's about a 2-year walk just to make that analysis. And now it's so much better. At the time, all we could do with Amanda was say, the neutrino came from somewhere over there. Is that a good telescope? No. Junk. And at this press conference in July, we now have it down to the neutrino, bunch of neutrinos came from this galaxy 3 billion light years away. That's much smaller than a grain of sand held at arm's length. That's how good we've got at aiming this telescope. It's pretty good. I think this would be a good moment to switch out of this and show this movie. Will the sound show up?
It will, yep.
And the movie is a little bit low res, and I guess I would ask you to also think about that in terms of
I'm gonna compete for the mouse here.
okay.
Ultimately, I will win.
Oh, I see how this goes. Okay.
You have to turn on the computer sound there.
And let's see. Not that one. Here we go. So, I'll give you a little intro to this, and I'll full screen it as well. But a lot of people ask me, why are they sending you to the South Pole? And there was actually an evening we were sitting around in the lab at the South Pole, and I asked that to the scientist I was sitting next to. I said, why do you think they send a teacher to the South Pole? And he thought about it for a moment, and he said, you know, until you got here and started asking questions, I didn't know what any of these other people right here in this room did on the project. Never thought to ask them. So I've learned something. Another thing I like to say is I'll go shovel snow, because it's funny because there's 2 miles of snow, so what chance do I have of winning? But in fact, we have a lot of maintenance issues at the South Pole. It doesn't snow a lot, but the wind picks up that snow dust and it covers everything, including scientific apparatus. There are bulldozers during the summer working constantly moving all of that downwind of the station so things don't get buried. But there's places where you gotta have actual humans get in there with a shovel and just dig stuff out. I will shovel some snow, I'm sure of it. And another thing that I'll end up doing is all kinds of stuff I couldn't have imagined. A week ago, I couldn't have imagined having this GoPro Fusion in hand and shooting 360-degree movies, but a guy at Purdue University asked if I would take the cameras and do that, and I like photography and do a lot of it, and yeah, I'm your guy, I'll do that. This movie, I was stuck at McMurdo, which is the big US base on the coast, in 2002 with 2 IceCube folks, a scientist from Belgium and a scientist from Germany, and we hung out and I taught them how to eat Thanksgiving dinner. Do you know how to do that? I'm not sure. He's going blank here. You probably do, I'm thinking. Anyway, I showed them how to do that. we had this movie that was in German, and on my little old PowerBook G4, did you ever have one of those? PowerBook G4, old Mac. We
Never had one of those.
no, you're possibly too young, possibly. So at McMurdo, we were just hanging out in our gear, and we basically translated this into Russian and Spanish and Portuguese and French, and found people that were could speak all those languages, and so this is the English version of our little movie. Check it out.
The universe is full of mysteries. Only small parts of its vast variety can be glimpsed with the human eye. Using ingenious modern detection systems, scientists can unveil new visions of the cosmos. For some time, there's been a new window into the universe that permits us to see space in a totally different light: neutrino astronomy. In Antarctica, physicists from around the world operate a new type of neutrino telescope, consisting of 670 light sensors melted into the deep ice of the South Pole. Its name? Amanda. Amanda is an array of devices for detecting muons and neutrinos. A constant rain of cosmic rays flows through the universe: light, nuclei, neutrinos, and muons. Neutrinos are extremely small elementary particles that have an unusual feature. They rarely interact with ordinary matter. Light and nuclei are often swallowed by cosmic dust clouds, but neutrinos travel through space, almost unaffected. Trillions of neutrinos reach the Earth every second. As messengers from their place of origin, they carry information from very distant galaxies, supernova explosions, and other energetic events and undiscovered objects. Neutrinos are unaffected as they penetrate the Earth, and they can travel right through the core of our planet. Are they completely unaffected? Well, not quite. A microscopic view shows how the travel of these ghost particles can sometimes be stopped by an extremely rare collision with the nucleus of an atom. Here is a neutrino colliding with the water molecule of the Antarctic ice. This collision breaks the nucleus apart, and the neutrino converts to a muon, which is basically a heavy electron. From the side, you can see another view of the muon's birth. This particular muon we picked up by the detectors. Muons are able to travel several kilometers through the ice. You can recognize a muon that is traveling at nearly the speed of light by a cone of light that follows it. This cone is similar to a boat creating waves behind itself. Looking inside the light cone, you can see its structure. This light is known as Cherenkov radiation. The muon emits very faint blue light rays outward from its sides. Taken together, all these emitted rays form a hollow cone behind the muon. In the darkness of the Antarctic ice, this glow can be detected up to 100 meters away. The Amanda detector, frozen in a depth of 1,500 to 2,000 meters, is optimized in order to see this light. Amanda is built out of powerful light sensors which are packed in pressure-resistant glass spheres. Several hundred of these, attached to steel cables, have been placed more than a mile deep into the ice of the South Pole, where they watch for the faint signals from fast-moving particles. When a muon flies through the Amanda detector, each light sensor registers the passing cone of light within 1/billionth of a second. The sensors convert the light into electrical signals, which travel to computers at the ice surface. Scientists at the South Pole Amanda Center supervise the data recording and do initial analysis. Complex computer programs investigate the chronological order and intensity of the signals. From this information, scientists can calculate the most important information for any telescope, which direction the initial neutrino came from. Several hundred neutrino reactions have been detected in trial phases. In January 2000, scientists and engineers were able to finish the second phase of Amanda's expansion. There are now 670 light sensors in the ice, and in a few years, a much larger telescope with 5,000 light sensors will be built. This will be known as IceCube, as the finished detector will be a cube a kilometer on every side, the largest scientific instrument ever constructed. What will these tiny neutrino messengers reveal? Huge energy jets that generate cosmic radiation? The origin of the dark matter? The birth of a supernova? Or something totally different? Every time that humans have built a new way to see into the heavens, they have been surprised. Nature has a great imagination. What surprises will the cosmos reveal through Amanda and IceCube?
Cool. So, a couple things to kind of sum that up. It's called IceCube because we've got a cubic kilometer of instrumented ice. That is the largest scientific instrument humans have ever made in the deep ice at the South Pole. We say there at the end, every time humans have constructed a new way to see into the heavens, they have been surprised. And that is absolutely true. Galileo was surprised. What did he see when he pointed a telescope up at the sky? Anybody know any of this story? 400 years ago? Oh. Oh. What did he see?
Oh, was it Saturn?
Ah.
Saturn's travel.
Not exactly. He did observe Saturn. He could not figure out what he was looking at. In fact, he thought the planet had ears. Because there was nobody had any idea that there could be a thing like a ring structure. So he never figured that out, that his telescope was not good enough to do that. That came, what, 150 years later, give or take. He looked at Jupiter. What did he see there? Does anybody know that story? Yeah? Ah, and what were they doing?
Oh, they're orbiting around Jupiter.
But everything should be orbiting around the
Sun.
Earth, because it's where the most important things are. Yeah, that was a surprise. He also saw Venus had phases. He saw craters on the moon. It seems amazing that he would have to even point out, the moon has craters. We kind of look at it now and go, yeah, okay, I can almost see them with my naked eye, but there was a time. After World War II, British scientists, they got a hold of some surplus radar gear that had been developed in World War II because it had gotten so much better that you could get the old stuff for free. And they pointed it up at the sky. They were looking, hoping to find tracks. When a meteor goes through the sky, it ionizes the air, it makes it reflective, and you can actually pick up a radio signal, let's say if you're in London from Paris, reflected off that for a few seconds. Cool. Tracks of meteors. And they found, oh, the sun is giving off radio. Jupiter is giving off radio. All kinds of things are giving off radio. Nobody had any idea that radio astronomy could be a thing. It's a thing. Now we can detect gravity waves. Now we can detect neutrinos. We are into multi-messenger astronomy, and we're going to find out amazing things. Did you ever wonder what it would be like to live at a time when humans were discovering an incredible amount about the world? Like, oh, if I could only live in the age of discovery back when Columbus and Magellan were able to come to the New World and take people's stuff. No, you live right now, you live in an age of discovery. And it's very easy to think, oh, nobody appreciates science anymore, but in fact, we're doing amazing, amazing things. The IceCube neutrino telescope, I think it's a really interesting detail, actually looks down. It looks for neutrinos coming up through the Earth. Signals going that way. Isn't that weird? In fact, if I can click back to it, I'll show you the logo for the Amanda telescope. It just went by a moment ago. Yeah. It's a little hard to see in this resolution, but we've got the penguin and the little penguin baby dude, and they're actually looking down. This globe would be upside down from its normal orientation. Only neutrinos are going to make it through the Earth and get into the detector that way. Neutrinos are very hard to catch. What size net do you need if you are going to need to catch a certain number of fish? And the fish are extremely slippery and hard to catch. What size detector do you need? You need to catch some fish. The fish are slippery. They're hard to catch. What's the size of your net? You need to take these guys fishing, I think. You need a big net if you want to catch some slippery fish. A really big net. I mean, yeah, okay, the holes in the net have to be small, but the net has to be really big. Are we making this even bigger now? Yeah, of course we are. Are scientists ever satisfied? Okay, we're done here. We got no more questions. No. In fact, I was laughing because you borrowed this over the weekend, and it says, a century-old mystery solved at the South Pole. There's no solving anything. There's just answering one question and getting 6 more, right? I'm headed to the South Pole on the 23rd of November. I'll fly to New Zealand. At New Zealand, I will pick up a whole bunch of cold weather gear. And then I will fly from there to McMurdo on the coast. There are about 5,000 people at McMurdo. I've heard it described as a cross between a college town and a mining town. Yup, people have bands, there are bars, people work hard, they play hard. From there, I will fly to the South Pole, and I'll be there about two to 3 weeks, give or take. I will send you, I've got a page with all kinds of links about this project. It is possible, if the timing's right, that the next time we talk, I could be calling in to the class here, and you could see my face from the South Pole right there on the screen, and wouldn't that be exciting? And you could ask questions like, is it cold? And I would say, yes, it's cold, and yeah, and then we could get into more interesting things. That's kind of what I'm going to do. I'll tell you about a couple other things that I'm going to be involved with that I'm kind of excited about. One, has anybody ever messed around with an Arduino or coding of any kind, a little bit of robotics? Yeah. So I am a musician as well, and since I started playing in a Hawaiian band a number of years ago, I started taking my ukulele everywhere I go. So I was going to take a ukulele to the South Pole, and one thing led to another, and one of my former students, Jay, just like you guys, except that was 10 years ago, I guess. He's now teaching physics at the University of Washington, and as soon as he heard I was going to the South Pole, he was like, can I come along? Well, no, but let's get together and have a beer. And one thing led to another, and what we decided to do was make a ukulele in a case excuse me, that will collect environmental information, temperature, light, radiation, and it will respond to that by playing songs using servo motors and frets. Yeah, what an insane idea. Some of that could sound not like a song, but like junk. But what we're hoping is that A, we can get it sounding kind of cool, and B, we can make all of the code, which won't be that complicated, open source and available to anybody that's interested. Around the world, people will be following what I'm doing, and hopefully some people will take that code and modify it and send it back to me, and I will run their code and have the ukulele play their song at the South Pole. It's just a different way to sort of engage people and get them interested. I've always been interested in the